Hello, everyone. So first of all, thanks a lot for organizing this seminar and for inviting me. I'm, of course, really happy to speak here. So my talk is called How Long Does Infinite Width Last? And it's going to be about signal propagation in long-range linear recurrent models. So first, let me try to explain why people are now interested in such linear recurrent models from the point of view of how long-range sequence modeling developed over the last years. So by long-range sequence models here, I just mean machine learning or deep learning models that work on sequential data. So we have the inputs of the form x1, x2, all the way to xt. And we want to model long-range dependencies in these sequences. Okay, so we have a picture like this. All the way, let's say, in the 90s, people, or like the most popular models for sequential data were recurrent models, or recurrent neural networks, RNNs. And there are also famous RNN variants specifically for long-range sequences, such as the LSTM model. The basic structure of these models is that they keep the memory or the information about the previous inputs in the sequence by storing a hidden state vector, ht, and updating it over time. So we receive a new input and we update the hidden state at every time step. And because of this structure of recurrent models, the computational cost of such models is, roughly speaking, linear in the sequence length t. But the well-known problem with recurrent models is that they're prone to vanishing and exploding signals, which makes it hard to stabilize these models and train them over long-range tasks. And I will speak about this problem today quite a lot. But as you probably know, more recently, transformers have become perhaps the most popular architecture for sequential data. And in comparison with recurrent models, transformers need to store the representations of all the previous inputs in order to compute the attention matrix. And this makes the computational cost of transformers quadratic in the input sequence length t. So even though transformers perform really well in practice, the computational cost becomes really large on long-range tasks. And that's exactly why in the last years, people started to be interested once again in recurrent models for long-range sequences. And we have seen models like Mamba, which are recurrent models competitive on long-range data. So these modern recurrent models, they also rely on storing a hidden state, ht. And importantly, they use linear updates of the recurrent state for even more computational efficiency and for parallelism. So these models are exactly the linear recurrent models I want to speak about. They inherit the computational efficiency from classical recurrent models, but they also inherit the challenges with stability. So this recent interest in such models is specifically the motivation for a lot of questions I'm speaking about in this talk. Okay, so recurrent models are, you can see a basic structure of such models in the slide. They get an input xt at every time step t, and they update a hidden state that I will always denote ht based on the previous hidden state and the current input, right? And the important thing in recurrent models is that at every step, we use the same function to update the hidden state. And vanishing and exploding signals problem can happen in different components of recurrent models. For example, we say that the hidden states vanish if the norm of the hidden state tends to 0 as the sequence length or time t increases. Or we can say that hidden states explode if the norm of the hidden state grows to infinity with time. In this case, we have numerical instability. We cannot compute even the forward pass of the model, and we have a big problem, of course. The same instability may also happen in the model's gradients. They can explode or vanish, and then we cannot compute the backpropagation and cannot train a model, right? And another type of similar instability that may happen in sequence models is that the current hidden state forgets the past inputs. So it means that the dependence on the current state on inputs far in the past vanishes. Okay, and so in the literature, people have for a very long time recognized that this vanishing and exploding signals is a big problem in recurrent models. To illustrate this, here are two examples of papers. The first one is the famous LSTM paper from all the way back in 1997. So this paper is basically as old as me. And the second example is a very recent paper that introduced the linear recurrent unit model. So it's a very modern paper. But somehow both of these papers identify the vanishing and exploding signals as the problem that they want to solve with the methods they develop. And in classical recurrent models, such as in this LSTM paper, people try to ensure stability by architecture design. But in modern recurrent models, it seems like the focus is more on careful initialization and parameterization for stability. So over the last more than 20 years, people somehow developed a lot of different methods to ensure stability because they recognize that instability is a big problem in recurrent models. But now I want to ask a very simple question. Even before solving the instability, do we really understand when and why exploding or vanishing signals happen in recurrent networks? And of course, if I thought the answer is yes, then probably I wouldn't give this talk. So I will try to argue that our current theory is not very well suited to answer this question, actually. Okay, so now to illustrate the problem, I want to compare signal propagation in recurrent models and in feedforward models. In the last, let's say, 10 years, most of the signal propagation theory was developed in the so-called infinite width limit of neural networks. Here, the width of the network, meaning the number of neurons in the layer, tends to infinity. And now I want to compare how recurrent and feedforward networks behave in this limit, okay? So on the left-hand side, we have our linear recurrent network. It's the same structure as in the previous slide. The only difference is that now the updates are explicitly linear, and at every step, they are parameterized by the same weight matrix W. And on the right-hand side, we have a network of exactly the same structure, but instead of using the same matrix everywhere, we use different independent matrices across time steps. So to distinguish the feedforward model from the recurrent model, I put the tilde above the hidden state here. And one note, here I define the models with complex weights because in linear models, it's somehow common to use complex weight matrices, but I will also often speak about recurrent and real and complex models separately throughout the talk. Okay, so what I want to tell you about these two models. Turns out, maybe surprisingly, that at infinite width limit, the signal propagation in these models basically behaves the same. The theorem on the slide says that suppose we initialize both models with centered Gaussians of variance inverse proportional to the network's width, then in the limit, the norm of the hidden state divided by the width m in the recurrent model and in the feedforward model differs by this only by this small O of 1, which just vanishes in the infinite width limit. Okay, so we see that at least from the point of view of the standard infinite width theory that you would see throughout the current literature on signal propagation, recurrent models are not more unstable than the feedforward ones. So from this point of reasoning, one can say that, okay, if we can stabilize feedforward networks, we can also stabilize recurrent networks in exactly the same way. But in practice, we of course know that this is not true, right? People, I showed you, for 20 years knew that in recurrences, instability is a much bigger problem. And so this apparent contradiction is kind of what led me to study the questions that I present here. Okay, so in feedforward networks, it's well known that we can ensure stability using the famous Glorot initialization. I define it here. So Glorot initialization for a matrix W is just a Gaussian initialization with variance of 1 divided by n. For real matrices, we just take a normal Gaussian, and for complex Glorot initialization, we will consider centered proper Gaussians, which means that the real part and the complex part are independent and identical, and the total variance of the Gaussian is still 1 divided by n. And so let's see in what sense this Glorot initialization is stable for feedforward networks. So since in feedforward networks, the matrix WT at every time step t is independent from everything that the hidden state seen before, it's very easy to figure out how the signal propagation, or at least the norms of the hidden states, behave in such feedforward models. Basically, for any initialization that is Gaussian with the variance sigma squared divided by the width n, we can immediately write a recurrence where the norm of the new hidden state is equal to the norm of the previous hidden state multiplied by our sigma squared, and edit the norm of the new input. And unrolling this recurrence, we get this expression where the dependence of the norm of the hidden state on the input k steps back is multiplied by this term sigma to the power of 2k, right? So now, from this form, we immediately see how it behaves depending on the different sigma values, right? So there's 3 possible cases here. The first one, where sigma w square is larger than 1, means that the impact of all the past inputs explodes with larger k, and the norm of the complete hidden state also explodes, right? So that's not a good case. Then second case, where sigma square is smaller than 1, means that the input of the previous impact of the past inputs vanishes. So this is forgetting of the past inputs, and the total norm of the hidden state converges to a constant. Now, Glorot initialization is exactly the only possible choice in the middle of these 2 cases, where the contributions of past inputs are stable, and the norm of the hidden state grows linearly with the time t. So we see that the norm here still grows in the sequence model, but it grows somehow benignly, not exponentially in the sequence length t. Now, the big question. So is this Glorot initialization that is stable for feedforward networks actually stable for long-range linear recurrent networks? We saw that from the point of view of infinite width theory, the answer should be yes. But if you look at modern papers on recurrent models, they do use Glorot as a baseline, but they always need to add an extra rescaling on top of this Glorot initialization to ensure stability. Because vanilla Glorot actually usually explodes in practice. But somehow there has never been an explanation in the literature why it explodes. And now I want to tell you that there is a nice way to see, like nice intuitive way to see why Glorot actually should explode, also theoretically. So remember our linear recurrent network with the hidden state HT, and let's just write it as in its unrolled form, which depends on the moments of our weight matrix W, right? So we see that the whole signal propagation just is controlled by matrix moments in linear models. So to see how this hidden state behaves, we may look at the spectrum of the matrix W. And the theorem on the slide, it basically characterizes the spectral radius, or the largest eigenvalue of the Glorot initialized matrix W. What the theorem says is also summarized on the right-hand side on the figure. So basically, in the infinite width limit, if we look at the Glorot initialized matrix, the whole spectrum of the matrix lies within the unit circle on the complex plane. These are non-Hermitian matrices, by the way, so the eigenvalues are always complex. And at infinite widths, we have the famous circular law, which says that the spectral radius is just 1. But now a maybe less well-known fact is that at finite width or finite matrix size n, there is a small correction to the circular law that makes the largest eigenvalue of W a bit larger than 1. And roughly the size of this finite width correction is the order of 1 divided by square root of n. The theorem here, it gives also the exact expression for this correction. And on top of this, it tells us that the distribution of the spectral radius is Gumbel. And this is true for both complex and real matrices. Okay, so looking at this theorem, we can immediately see that it already suggests instability in the hidden states as long as the sequence length t reaches the square root of the width n. Because when we multiply such eigenvalues a little bit larger than 1 over many recurrent steps of the network, this finite width correction accumulates, right? So that's, I think, already a good intuition, but now let me maybe make it more precise how this spectral effect leads to exploding signals under Glorot initialization. So we have this lemma here that tells us how effects of past inputs explode in linear recurrent networks in the joint scaling limit of the width n and sequence length t, where the scaling is such that t grows proportionally to the square root of n. And the result tells us that suppose we have our Glorot matrix W, we take its t moment, multiply it by some input u, and then the properly rescaled norm squared grows at least exponentially in our alpha squared, which is the ratio between the sequence length and the square root of width. And the proof here, like knowing the spectral intuition which I just told you, proof is pretty easy. Basically, this squared norm is controlled by the mean squared singular value of the matrix moment Wt. But the mean squared singular value is just lower bounded by the mean squared eigenvalue. And as we just saw, the mean squared eigenvalue for large sequence length t will be just dominated by largest eigenvalues, which are larger than 1 by something of order of 1 divided by square root of n. Yeah, so of course, I don't write everything here in the paper that I cite. We also figure out the exact expression using some random matrix theory, but the logic is just this. And from this lemma, we can immediately figure out how the actual hidden state in linear recurrent models behaves. So if we look at our rescaled norm of the hidden state, it will also grow exponentially in this term t squared divided by n in the joint scaling limit. And this already tells us that Glorot explodes, right? So let's look again carefully at this result that I just showed you that Glorot explodes. So here, just reminding that we are considering the joint scaling limit, where the widths n and the sequence length t grow together with a given scaling. And this, as you can see in the figure, gives us exponential growth in the hidden state norm for large enough sequence lengths. But remember that in the infinite width limit, from the analogy with feedforward networks, the norm of the hidden state may only grow linearly with the sequence length t. So we see that the pictures here, they compare results of the classical infinite width analysis that you will find throughout the literature and our joint scaling analysis on these long-range recurrent models. What we see is that the joint scaling analysis reveals instability of Glorot initialization that's completely hidden by the infinite width analysis. And also, maybe even more interestingly, this analysis shows us the difference between recurrent and feedforward signal propagation that we couldn't see at infinite width. Okay. And based on this theoretical understanding of why Glorot actually explodes in practice, we can also directly come up with a principled way to rescale Glorot initialization to ensure that it doesn't explode. So you remember that the spectral radius according to our theorem from the beginning, is a Gumbel variable. So we can just rescale our Glorot initialization based on Gumbel quantiles. Suppose AP is a P quantile of the Gumbel distribution, and then it gives us a rough upper bound on the spectral radius using this quantile for large weight matrices. Then we can just use this upper bound to rescale our vanilla Glorot initialization. And this ensures that the spectral radius stays below 1 with a certain probability and allows us to mitigate exploding behavior with this probability. So the argument is that this kind of rescaling replaces the ad hoc rescaling used in the literature so far. Okay, so now up to this point, I only gave you this spectral intuition, which was nice and simple. I think it's pretty easy to understand it, but it could only give us a crude lower bound on the growth of the signal in recurrent networks. So now I want to tell you about newer results that are much more precise in the sense that they give us exact finite-width behavior of signal propagation in linear recurrent networks. Okay, so it's a complicated theorem. Basically, what we have here is that we define two signal energies just for notation. This energy S and T is just our finite-width norm of the hidden state divided by n. And Q and K, it's the impact of an input U after K recurrent steps, right? So the theorem on the slide tells us that for complex Gaussian for complex Glorot initialization under fairly general input sequences, we only require, for simplicity, that they are whitened, which is also not necessary here. But basically, the input sequences don't have to have any independence across time. It's a pretty general result. So we have that we can figure out the exact closed formed expressions for both signal energies S and Q for any finite N, T, and K. Okay, and the expressions are in the theorem. They are a little bit complicated. Here in the Q, for example, we have the difference of the rising factorial and the falling factorial. And these expressions look like that because they come from combinatoric reasoning here. So maybe it's hard to understand from this theorem how they behave. So maybe let's better look at the pictures. So here you see how the energy S and also the energy Q behaves depending on how we scale the sequence lengths together with the network's width n. And in both pictures, I separate the behavior of these energies into three different regimes. The first one I call the subcritical regime. Here, the sequence length grows slower than the square root of n. In this regime, throughout this regime, infinite width predictions actually hold. And in particular, Glorot initialization should be stable in the same sense as in feedforward networks. Like you see here in this regime, our energy S and T grows linearly with T, as should be at infinite widths. Now, exactly at the critical regime, where sequence length scales to the square root of widths, finite width deviations become order 1. So here, the behavior becomes qualitatively different from the infinite width predictions. And finally, there's also a supercritical regime where the sequence length grows faster than square root of n. In this regime, the finite width effects dominate, and in particular, we would have rapidly exploding signals in something like Glorot initialization. So somehow together, these results now give a precise answer to the title question of this talk. If the question is how long does infinite width last? We see that here it lasts exactly until the sequence length reaches the order of square root of n. In the paper, we also give expressions for how the signal energies behave under all these scaling regimes, like how signal energies grow in each of them. But perhaps the most interesting one is the critical regime, because here we have a non-trivial finite limit for signal energies. So the expression for the energy Q here, it involves this hyperbolic sinus, and the expression for the cumulative signal energy S&T, we can get it by integrating our sinus. And this happens at the critical regime where the width T, the sequence length T grows as square root of width N. And this expression is nice because basically it allows us to compare. It gives us a simple formula that we can already use in practice to understand how signal propagation behaves. So here in the figures, you see empirical results for various finite values of the width N and the sequence length T, plotted against the theoretical expressions for the critical limit. And you see that for a broad range of finite networks, this critical limit expression already gives us a good enough approximation of the practice. So we don't necessarily need to compute all the factorials that I showed you before. It's enough to look at much simpler expressions here at the critical limit. Another thing to note is that the results, these sharpest results I showed you so far were for complex weights, but the reasoning in the paper also directly gives us a lower bound for the real weights. Basically, if we imagine an identical model, identical linear recurrent model with real weight matrices, the signals in such model will grow only faster than in the complex model. And here is also the empirical verification of this statement. What you see here is the empirical signal energies for real recurrent models plotted against the critical limit or the complex case. So indeed, the real case explodes faster than the complex case. Okay, now at the end, maybe I would like to give you just a very rough idea of the method we use in the proof here of such results. And I would again focus on the difference between feedforward and recurrent networks to explain why the recurrent case is much more challenging. So in general, to figure out how signal propagation behave, we need to understand how the mean squared singular value behaves. And here in the slide, I just tried this mean squared singular value as a trace of a long matrix product for feedforward networks. And I can also expand the trace using the sum over the indices of the matrices involved in this matrix product. So far, nothing happened. We just replaced this trace with a sum. But maybe one thing to notice is that since we are dealing with the complex case, there is one conjugated entry for every layer of the network. And there is one corresponding non-conjugated entry for every layer. Okay, now we have a big sum of expectations of Gaussian monomials. And as usual, we can apply Wick theorem to this expectation. The Wick theorem lets us rewrite the expectation of a Gaussian monomial as a sum over possible pairings of the Gaussian entries in the big product. And for every pairing, we need to consider the product of the covariances generated by this pairing. So maybe you've never seen this. It's a little bit scary, but the idea is actually pretty simple. And this is basically a standard way to convert these linear algebra problems into more like combinatorial problems. So for recurrent networks, everything is particularly simple here because actually in this sum that we have in the Wick theorem, where we consider all the possible pairs of the Gaussian entries in this long product, the only entry that gives us a non-zero covariance product is the so-called ladder pairing, that for every matrix of a given layer pairs it to the non-conjugated matrix of the same layer. Okay, and this is just because in the feedforward case, all the matrices are independent between layers. So therefore, this sum just ends up being a single term, and we can calculate the contribution of the single term. And after simplifying everything, we just get that this long trace is equal to 1. Okay, so this is for feedforward networks. But now let's look at the recurrent case. So in the recurrent case, instead of the product of many independent matrices, we would have a matrix moment WT, right? Now, once again, rewriting it using the matrix indices, gives us a very similar expression, but now our problem is all the matrices are, or all the entries are potentially dependent here. So instead of only caring about a single ladder pairing that was important in the feedforward case, now we somehow have to account for much more possible pairings. And now the problem moves much more towards understanding what kind of pairings are possible and what is their contribution from the weak theorem point of view. So basically, now in the recurrent case, we need to think of the sum over pairings, where each pairing has a certain contribution based on how many matrix indices it contracts. And I'm not going to explain here how exactly we figured this out. It's in the end, you can see the paper to see the actual method. But the interesting conclusion maybe is that, so we have the first order 1 contribution from the ladder pairing, but the second non-trivial contribution in the recurrent case has this form of proportional to t squared divided by t to the power of 4 by n squared. So you see that this term doesn't vanish anymore when we have our sequence length t growing as the square root of the width n, right? And maybe this term can also be interesting from the point of view that the first correction is not of order n, but of the order of 1 divided by n squared right away. Okay, so let me summarize everything that I said so far. So we saw that stability is an important problem in long-range recurrent models, but the theoretical understanding seems to be somehow limited by reliance of the signal propagation theory on the infinite width limit. And in the infinite width limit, where the sequence length is fixed while width tends to infinity, we saw that recurrent and feedforward models behave the same from the signal propagation point of view. And this means in particular that standard Glorot initialization is predicted to be stable in long-range linear recurrences. But then we looked at our more refined joint scaling analysis, where we saw that infinite width predictions actually only hold when the sequence lengths are not larger than, are smaller than square root of width n. And as long as our sequence length scales larger, scales faster than this, infinite width predictions generally break. And this means in particular that Glorot initialization becomes unstable in this case. And we also start seeing the qualitative difference between feedforward and recurrent models that we didn't see at infinite width. So overall, this highlights that our finite width and joint scaling analysis better captures the realistic performance of long-range recurrent models. And also in general, it shows maybe the benefit of going beyond the infinite width theory in long-range problems. Okay, so that was it. Thank you for your attention, and I would be happy to take questions.